So far we've looked at different kinds of interactions. We've looked at ये दूसरा नहीं, बहुत छोटी, बहुत दूसरा नहीं, दूसरा किधर गया है? ये बहुत सेम टांग है, छोटी टांग है। All right, so it's very hard to move one's head with this. चलें कोशिश करते हैं। हल्क पे जिंदगी का
सर अभी बेल्ट के साथ उसको लगा
हैं, इधर बेल्ट के साथ लगा। Alright, so we've looked at the dipolar interaction between spins. We've also investigated the exchange interaction in quite a bit of detail. And then we've looked at the spin-orbit interaction. And then in the previous two lectures, we looked at the crystal field interaction. So all of these are different kinds of interactions that we've introduced successively as interactions between spins. This is an interaction of a charged particle, which is the charge on the cation, in an environment of negatively charged anions. All of these, as you know, with the exception of this, are electrostatic interactions. This is an interaction between two magnetic dipoles. This is primarily an electrostatic interaction. This is primarily an electrostatic interaction. But the spin degree of freedom comes in through the symmetrization postulate. Spin-orbit interaction is a relativistic effect. So we've looked at all of these effects. Now what we would like to talk about is something more general, and we would like to introduce the concept of a solid. Suppose there is a single electron in a solid, okay? And we would like to come up with a general Hamiltonian for such an electron. Now if you look at the electron inside a solid, its Hamiltonian will be p square over 2m plus the potential energy term, which could be a periodic potential inside the solid. Now we might even have the interaction of the spin of that electron with some external imposed magnetic field, which means that we could have a term of this kind, the magnetic moment of the electron interacting with an external field. Right? We could also have an electric field that is imposed on the solid. And by virtue of the electric field, there could be an electrostatic term which is given by this. So this is the general case of what happens when an electron is present inside a solid. This is the crystalline potential, the potential due to the ions. This is the kinetic energy of the electron. This is a Zeeman term, the interaction of the magnetic moment of that single electron with an externally imposed field. This is an electric term. We could also have spin-orbit interaction inside the same solid. And if we include a term for the spin-orbit interaction, we get 1 over 2c E cross V, which is del phi. This becomes plus crossed with the momentum m V. Okay? Interacting with the spin of S of the electron. Okay? So this is really an electric field into speed, into velocity, which comes out from relativity. We've already looked at this, and this gives us an effective magnetic field that's interacting with the spin of the electron. So all of these terms can exist inside a solid. However, if we have that single electron inside a metal, which electron are we talking about? There are electrons that are free, and there are electrons that are part of the core of the nucleus of the atom. So there are bound electrons and there are free electrons. Now this formalism applies to any electron whatsoever. Okay. Now what we've seen is that the inner shells of the atoms, that is the core electrons, which are not part of the valence shell, overall those shells are completely filled. Therefore, their orbital angular momentum and the spin must be zero. Do they contribute to magnetism? This is the question. So what we're going to look at first is the concept of bound electrons. Electrons that are part of the atom, they are not mobile, and we would like to see whether they are contributing to magnetism in one way or the other or not. Okay? So this is a very general Hamiltonian. One modification that we have to make is that the electron is a charged particle. When a charged particle is present inside a magnetic field, this momentum P becomes the canonical momentum, and it is replaced by P plus QA, where A is the magnetic vector potential. This you learn from your quantum mechanics. Now the charge on an electron is minus E, so this becomes P. This is P minus QA, this becomes P plus EA. So we have to replace this P by this term if a magnetic field is present. And this P will also appear in the spin-orbit interaction term. So each one of these P's has to be replaced by this in the presence of a magnetic field. Now what is A? A is the magnetic vector potential. And since del dot B is 0, which is Gauss's law for magnetism, this means that B must be the curl of another vector field. That vector field is the vector potential, because the divergence of a curl is 0, so this must be the curl of some other vector. This is called the vector potential. Now, there is a freedom in what kind of A would you like to choose, and that choice is called the choice of the gauge. So one choice of the gauge is the symmetric gauge. So remember that B is the physical measurable. By changing A somehow in some proper fashion, B does not change, which means that we have the freedom to choose A. There is some freedom to choose A. Okay, and it does not, the freedom, the non-uniqueness of A does not affect physical reality. So we choose a gauge. That is, a gauge that we choose is called the symmetric gauge. In the symmetric gauge, A is given by 1/2 of B crossed with R. This is called the symmetric gauge. Now you could prove, one could prove that this particular A, when you take the curl of this will reproduce B. Okay, we can prove that. Suppose our B is constant. It does not change with space, it's uniform everywhere. So what we would like to do is we would like to insert this value of P in here, that this becomes a canonical momentum, and we would like to use this choice of gauge, and we would like to modify this Hamiltonian, and we would like to find out what's the energy of the charged particle in the presence of a magnetic field. Okay, and we'll derive a completely general result. So this looks, all of this looks tedious, but please bear with me. The journey is going to be tortuous, but the result is going to be splendid. So now if B is constant, first of all I would like to argue that this is a good choice of A. It's a legitimate choice of A. For that I have to prove that if I take the curl of this, I recover B. Okay, I have to prove that. So what I would like to do is, I would like to find the curl of this, the curl of A. Okay, this I would like to find. And it's a vector, so I find one of the components. Okay, now I use the Levi-Civita symbolism, I, J, K. This is the partial derivative with respect to J. This is the kth term of A. A in itself is a vector. So I take the kth term of A, I, J, K, partial J. Now what's the kth term of A? The half comes in here. The kth term of this vector is K, L, M. K, L, M, B's Lth term and R's Mth term. So I'm finding, and I would like to argue that this should equal the ith term of the vector B. Okay, because I want to prove that del cross A is equal to B. So I'm proving that this is a good choice of, is a legitimate choice of the gauge. Sure.
Sir, for the general Hamiltonian for the solid, do the exchange interaction terms arise out of it happening?
Yes, they do. But right now, we're not dealing with exchange in this particular case because we're talking about a single electron that's inside the solid. So there's no question of exchange in our discussion right now. Alright, so let's prove this. So 1/2 I, J, K. This Levi-Civita symbol is a constant. I can take this out, K, L, M. And now I need the derivative with respect to J of B, L, R, M. Now I use an identity. This thing over here is del, the Canonical delta JL, Canonical delta Km minus Canonical delta Jm, Canonical delta KL. Partial J, BL, Rm. This equals 1/2 of partial J, partial delta JL, delta Km, partial J, BL, Rm minus delta Jm, delta KL, partial J of BL, Rm. Now I impose the conditions given out by the Canonical delta functions. 1/2. Now this J, this L must be equal to J. So partial J of B, J, M must be equal to K. So RK minus partial J. This L I would like to, this L must be equal to K, so I have BK, and M must be equal to J, so I have RJ. Okay? Now this gives me half partial j bj rk plus bj partial j rk. Okay, I employ the derivative rule, minus partial j bk rj minus bk partial j rj. Okay. Now what is this partial j bj? Yeah, del dot b. What's del dot b? 0 by Maxwell's equation. Now, what is this partial j bk? The field is constant. It's uniform in space. This must be 0 as well. This is 0. What is this thing equal to? Partial j rj. 3. The number 3. It's partial x partial x plus partial y. So it's 3. So this term is minus 3 minus 3 b k partial ijk partial k lm jlkm minus jmkl partial jblrm. This is partial jl partial km partial jblrm minus partial jm partial kf partial jblrm. This is partial j b j r k minus partial j b k r m is j. Okay, this is 0. Now what is this particular term over here? Partial j r k. This is a Canonical delta function. This is delta jk. So I have bj delta jk, correct, minus 3 times and of course here I also have this jk. Here I have delta kj. Okay, so I have minus 3 bk here. So I am, I think, missing out something over here. J just a minute, please. Where is my... Oh, one problem. Okay, so what I've missed out here is, in order to apply this identity, this must, I would like to replace this with delta Kij. Okay, I would just like to change the orders. So epsilon ijk equals epsilon kij. If I preserve the order and just rotate the variables, then this does not change. Then I can apply the identity. So this is ekij into eklm. So this becomes, I'm sorry about that, so sorry. This becomes iljm. Sorry about that. This becomes imjl. Sorry. ILJM. IMJL. Okay? So this equals this thing. If this multiplied by this equals this is an identity. Now I can apply my rules over here. J is partial J. Now L is equal to I. See? L must equal I. M must equal J minus partial J. L must equal J, and this M must equal I. Sorry about that. Now I can partial J Bi, partial J Bi, Rj plus Bi partial J Rj minus partial J Bj Ri minus Bj partial J Ri. Okay, so this is the correct prescription. This thing is zero, still zero because the field is uniform. This thing is zero because the divergence of B is zero. Now let's look at these terms over here. This thing is 3 times Bi, okay? And this thing is minus Bj delta Ij. So this is really 3Bi, J must equal I, 3Bi minus 2Pi, which is Bi. 3 minus Bi, which is 2Bi, divided by 2, this gives us Bi, which is the desired result. Hence, this choice of gauge is a legitimate choice. Okay? So now we would like to insert this value of A into the Hamiltonian. Remember, we have the destination in our mind. So it's going to be a pleasant surprise at the end. So the Hamiltonian is P plus EA square over 2M plus VR. Okay? This is an operator, R. And what I could do, I could write the operator here and present this as a vector. Now what I'm going to do, minus mu dot B. For an electron, mu equals E over M, minus E over M. So plus E over M S dotted with B. This is what we have for an electron. Now I suppose that I have not applied an external electric field. So my phi is 0. And I'm ignoring the spin-orbit interaction for the time. So this is my Hamiltonian. Now if you look at this Hamiltonian, I have to expand this. When I expand this, I get P square over 2M plus VR plus plus square of this. Okay, So plus square of this is E square over 2m then I have other terms. I have a term, so I'm going to write this on the next blackboard over here, plus additional terms. So I have a term which is 1 over 2m P dotted with EA plus 1 over 2m EA dotted with P. These are operators, so I don't know about the commutation relations at the moment. Plus the Zeeman term, E over m S dotted with P. So this is my Hamiltonian. Now these terms over here, if a magnetic field were not imposed, this is the native Hamiltonian. Let's call this H naught. This is the Hamiltonian in the absence of a magnetic field. So my H is now H naught plus these additional terms, E square over 2m A squared plus 1 over 2m, I take E as common, I need to figure this out, P dotted with A plus A dotted with P plus the Zeeman term, how the spin interacts with the field itself. Okay? Now this is the term that I need to look at. This is my Hamiltonian. This term over here is somewhat clear because I have an expression for A. This term is E square over 2m. My A is half into B crossed with R. So this term is really 1 over 4 B crossed with R modulus square. So this term is somewhat clear. Now I need to figure out these terms over here. Okay, now let's do that. Okay. Now first consider, if I consider P dot with A, okay, the dot product of these operators, this is Pi AI. These are operators all the time. Now Pi, what is AI? AI is half into B crossed with R. So the Ix term is equal to epsilon ijk bj rk. This is P dot A. Now I'm still preserving the order of these operators. This is the position operator, this is the momentum operator. So this is half epsilon ijk. This is now just a scalar, it can go anywhere. Bj. Now I'm preserving the order between this momentum and the position operator. Pi rk. Now look at this term. What's the commutator between the position and the momentum operator? What is Pi rk equal to? Is the minus iota h bar Canonical delta ik, right? This is 0 if I is not equal to k. Otherwise it's equal to minus iota h bar. Now, so this term, the commutator is 0 if the commutator is 0 if I is unequal to k. Now if I is unequal to k, the commutator is 0, so I can reverse the order. When the commutator is 0, I can reverse the order, it doesn't matter. I can reverse the order of two operators when the commutator is 0. But the commutator is not, I can be equal to k. But look at this symbol over here. This symbol dictates that this term is 0 if I equals k. If any two indices are equal, then this term is 0. Right? This term is defined in a fashion that whenever two indices are equal, the term goes to 0. So if this term is to exist, if this term is to exist, I must be different from k. And when I is different from k, then these two mutually, these are compatible observables. They commute, because px commutes with x, y, px commutes with z. So I can reverse the order. So when I reverse the order, I can always write p before and r after, or I can swap the order, which would mean that p dot a is the same as a dot p. So if I do a similar calculation for a dotted with p, I will get the same result. So the order of p and r is unimportant here. This is the way we defined or chosen our gauge. Hence, this p and a commute with one another. And when they commute with one another, I can write my Hamiltonian as h equals h naught plus e square over 8m b crossed with the r operator modulus squared, plus this becomes e over m p dotted with a. Now what is a? A is 1/2 b crossed with r, okay, plus e over m s dotted with b. This means this equals h naught plus e square over 8m. This is a purely quantum mechanical calculation, plus e over 2m. Now I can use the properties of the vector identities. What I could do, I could take b to the back, r to the so what I could do is actually I can write this thing as b crossed with r dotted with p. What I could do, I could write this as r crossed with p dotted with b, right? It's the property of the dot product. I just have to preserve the ordering BRP, BRP. What is R cross P? It is the orbital angular momentum of the electron. Bound or free, we don't care at the moment. This is the orbital angular momentum of the electron. Each electron will have an orbital angular momentum, may have an orbital angular momentum. So this is L dotted with B. So this thing is actually L dotted with B. And I have E over M S dotted with B. So look at this factor, there's an E over 2m here and there's an E over m here. That's because the lambda G factor for the spin of electron is 2. So there is actually G here, which is 2. So 2 over 2 just cancels away. So now let's write this in a more amenable fashion. What we have here is H, the Hamiltonian for an electron, which is a charged particle inside a magnetic field, is H naught, the native Hamiltonian, plus this term, and we have to figure out what this term means. B dotted with R modulus squared plus E over 2m L plus 2s dotted with B. This is just the lambda G factor for a single spin half particle. Now what is this term over here? This term is just the interaction of the orbital angular momentum and the spin angular momentum with the magnetic field, and this is what we've already looked at. This is the paramagnetic term. So this term accounts for paramagnetism of bound electrons, and we've already studied paramagnetism in detail. This is just the background Hamiltonian. Now what does this term represent? This term does not have an orbital or a spin angular momentum. It's there for every electron. Whether it does have an orbital or spin or it doesn't. That electron will always give a term of, an electron will always give a term of this kind. This is called the diamagnetic term. And this leads to the effect which is labeled as diamagnetism. So all electrons, no matter where they belong inside the solid, they may or may not account for paramagnetism because they may or may not have orbital angular momentum. The spins can add up to 0, but all of them will show a diamagnetic effect. So diamagnetism is a ubiquitous effect. It's a more universal effect. It's always there. It can be overcome or overshadowed by other effects, but it's always there. And if you want to see this effect in a solid, you really have to switch off other effects because this is such a small effect. Okay, so everything is diamagnetic. And if it's not paramagnetic, the diamagnetic effects can be made rendered visible. Now let's look at what does this effect mean. What is diamagnetism? We know that paramagnetism means that you have a collection of spins, you impose a field, and then there are energy differences between parallel and anti-parallel modes, and then you can find the magnetization and susceptibility. What does this mean? Remember that this is a purely quantum mechanical calculation that we've done so far. Now we would like to find out the meaning of this diamagnetic term and what does this represent? What kind of susceptibility does this cause? What, if you insert a magnetic field, what is the response of this term? Any questions? So what we would like to do is, we would like to investigate this diamagnetic effect. Remember, we're talking about bound electrons at the moment. Now, this is like a perturbation to the Hamiltonian. So we can find corrections to the energy. This gives us the native energies. Suppose the paramagnetic effect is not there because L is 0. For a single electron, we cannot switch on off S, but let's look at purely this effect. So we would like to find out the corrections to the energy due to this perturbative Hamiltonian, and we'd like to use first order perturbation theory. So the corrections to the energy to the first order due to this diamagnetic effect. Suppose the electron is in its ground state. Okay, so we want to find out the corrections to the energy in the ground state due to this term. So by first order perturbation theory, the corrections are, suppose the ground state I label as ket 0. Okay, this is my label for the ground state, whatever it is. This could be an electron in the s orbital of a hydrogen atom if you talk about the gas of hydrogen atoms. Now this correction is going to be this term E square over 8m bra 0 B crossed with R modulus square 0. Now let's suppose that our field is constant, B is constant, and this is applied in the z direction. So my field is B purely in the z direction. It's constant, so I take that direction to be the z direction without loss of generality. Now B crossed with R. Let's do something which is slightly childish. Ex, Ey, Ez. Remember, these are terms of the vector potential. So I have B crossed with R. This is 0, 0, B, X, Y, Z. So I have Ex minus YB minus Ey minus Bx. So I have B minus Yex plus X Ey. This is my B crossed with R. And it's called a symmetric gauge because with Ex there is a minus Y and with Ey there's an x. So there are both of these terms, and okay, so this is why it's called the symmetric case. This is the x component of A, this is the y component of A, the vector potential. Now I put this in here, that's all I need to do. When I put this in here, I get E square over 8m. This b, I take the square, it's a scalar, I can take it out, 0. Now I take the square of this, I get 0. And I need the expectation value of x square, y square operators. This is my correction to the energy. First order correction. Now suppose my electron is in a spherically symmetric orbital, so to say. It's a bound electron, but it's spherically symmetric orbital. In that case, we know that x square equals y square equals z square. If it's in a spherically symmetric potential, then the expectation value of these operators is going to be the same. And each one of them, this is going to give us 1/2 of r square, where r is the position vector operator. It's this all, right? So what I could do, then x square plus y square is 2/3 of r square. Right? So this becomes E square 8m b square 2/3 0 r square 0. This is E square b square over 6m expectation value of r square. This is the correction to the energy. And if I want to find out this correction to the energy, I need to find out what the ground state is. That ground state could be the 1s orbital. If it's the 1s orbital, I put the wave function for the 1s orbital over here and construct the integral, and I can find out the corrections. I can find out numerical values if I know the mass of the electron and I know what the field is. Now you observe here that this correction to the energy is proportional to b squared. The correction to the energy imposed by the paramagnetic term must be proportional to b. So for low fields, for low magnetic fields, b square is much smaller than b. So for low fields, the diamagnetic term is swamped by the paramagnetic term. The paramagnetic term is much bigger. First, there is the b square dependence. Secondly, there is no temperature dependence here. We know that here, for paramagnetism, it depends upon temperature. We've looked at the Brillouin function. This is purely temperature independent. Okay? And this exists for all electrons inside the system. If there are multiple electrons in the system, then each one of the electrons, you put in the quantum state of each electron and sum up over all these expectation values. Okay? And you put in the exact value of r squares for each one of the electrons. Okay? So from this energy we can also calculate the magnetization and the susceptibility. Okay? So how do we do that? The magnetization is, we'll learn when we talk about thermodynamics, the magnetization is given by, you have to take into account the number of electrons per unit volume. You put in a minus sign and you take the derivative with respect to the magnetic field of the free energy. नहीं, with respect to B होगा. नहीं, ये magnetism with respect to B है. ठीक है? F is, as you all know, is given by E minus Ts. So at 0 Kelvin, when T is 0, the free energy is the same as the internal energy of the system. So this is the energy of, this is the correction to the energy. If I take the derivative of this with respect to B and multiply it with the number of electrons per unit volume inside the system, and then right now I'm assuming that all of the electrons have the same R squared. This is my assumption right now. Then I can find the magnetization. So the magnetization turns out to be minus N. I take the derivative of this with respect to B, get 2E square B over 6M. This is, yes. So this is minus N E square B over 3M, 0 R square. Here my assumption is that all of the electrons in the system have the same expectation value in the ground state for this R square. So all of the electrons are the same. Okay? So this is my magnetization. And if I would like to calculate the susceptibility is given by M over H. H is B over mu naught, right? So the susceptibility, the diamagnetic susceptibility, is given by mu naught minus N mu naught E square B over 3, the mass of the electron independent of temperature, weakly dependent on the magnetic field, the negative sign. So if I were to make a plot of the susceptibilities versus 1 over temperature, for paramagnetic materials we know that chi is inversely proportional to temperature, the Curie's law. So this thing versus this will give us a straight line positive for paramagnets, right? Or if I were to plot chi versus T for paramagnets, the curve will look like this, right? Curie's law. For diamagnets, the susceptibility is negative and it's constant and a very small value. This is for diamagnets, almost constant with temperature. And the assumption breaks down because sometimes it breaks down because we only consider the first order perturbation theory. There could be cases when the higher order terms are important. Okay, so this is the diamagnetic effect, which is a ubiquitous effect, universal effect present everywhere. It does have a dependence upon B. So if I make a plot between the susceptibility and B for a diamagnet, you will see a slope. So increase B, there will be a slope. Okay? So this is the diamagnetic effect, and if you have many electrons, the correction to the energy due to all of the electrons, the first order term, will simply be given by E square B square over 6M sum over all the electrons, all the Z electrons inside the atom. But we assume that each one of them is in the ground state. So we write down the respective ground state of each of the electrons. R I square. This will give us the diamagnetic susceptibility of the entire bunch of bound electrons. And if each electron is in the same state, it is the same ground state, and at the same distance from the nucleus, which means in the same orbital, then this term will be capital Z times the diamagnetism of a single electron. So that's how, if you would like to plot sometimes, if you would like to plot the diamagnetic energies, which will give rise to different diamagnetic susceptibilities versus the atomic number, higher the Z, higher will be the susceptibilities on a straight line, roughly. Okay, so now this is only considering the first order perturbation term. If one does consider the higher order terms, then things might get slightly complicated. So if I would just to write down the expression for the second order term, then what I need to do is this would become, by second order perturbation theory, this is E square over 8m sum over the nth state, a state above the excited state, n r square, the ground state, E modulus square En minus E naught, where I sum up over all the excited states. This is a second order perturbation term. This might become significant if there is significant overlap between the excited states and the ground state. And that is why when we looked at the table of paramagnetic susceptibilities, this term becomes important there. And the other thing is that if you compute the susceptibility with these terms, the susceptibility might turn out to be positive. So this might be a paramagnetic term. Okay. It might turn out as a paramagnetic term. So this kind of, so orbital effects. So this so-called diamagnetic term, this thing here, A square term, might lead to diamagnetism in the first order, and it might lead to paramagnetism in the higher order. Okay, but generally the diamagnetic term is largest. And the paramagnetic term for the excited states is only significant when this term has a substantial overlap, when this term is far away from zero. If the excited state has a big gap with respect to if this thing is large, then these terms are going to be small. If En is almost the same as the ground state, which means that the gap between the excited states and the ground state is small, then this term might become significant. This kind of paramagnetism, which does not result from a term of this kind, but which results from a term of this kind, is called Van Vleck paramagnetism. Van Vleck paramagnetism. And another thing that you observe, so there's a dependence upon the atomic number, there's a dependence upon the magnetic field, there's an independence of the temperature. All of these are hallmarks of diamagnetism. And another thing you might have noticed, there's a dependence upon R squared. So bigger this R squared, bigger will be the diamagnetic effect. So if the electron is in an atom, that's fine. But if the electron is part of a resonance ring in a benzene molecule, or an naphthalene molecule, or an anthracene molecule, or some bigger molecules, and the electron is in a state where its R square is really, really large, because it can traverse the entire landscape of the molecule. It's not confined to an atom. Or you have graphene, sheets of graphene, in which the electron is mobile over the entire sheet, then such materials can have large paramagnetic effects. So these are real effects which are seen in the laboratory, and all of these come out from quantum mechanics. Quantum mechanics is not there to be kept under lock and key. It's not there for termites who would eat up these books. It's there for reality. It does exist. Quantum mechanics is so powerful because it shows up in all of these different conditions. It always pops up and teases us. Now I would like to talk about some more effects. What I would now like to talk about is, yes?
So this dependence on V, it should be only up to a certain value of V because we treated that as a
Yes, it's a good point. Only up to small magnetic fields does the first order perturbation hold true. And only up to small fields does this relationship hold true. So all of this is valid under small fields. But the effect is so small that those fields could be several Teslas large. Okay? So mathematically, yes. Water, the most important solvent of life, is diamagnetic. Most metals are diamagnetic. Okay? Now what we would like to talk about is, we would like to relax this condition of bound electrons and we'll start talking about free electrons. So there are free electrons inside a metal. What kind of magnetism do they cause? Okay? So far what we've been looking at is localized magnetic moments. Localized moments which are latched onto definite positions. So these bound electrons are localized and they give rise to paramagnetic and diamagnetic effects. Now we would like to talk about free electrons or itinerant electrons. Itinerant electrons. Musafir electrons. Right? So now we would like to use the concepts of Sommerfeld's theory, which you learn in basic solid state physics. And I hope you are familiar with all of the details and nuances of that theory. And we know that these free electrons, as a result of their interaction, they follow certain statistics. So a quick recap of Sommerfeld's theory is that the electrons follow Fermi Dirac statistics. Zafar, aapne ye cheezein padhi nahi hai na ye? So in a metal we have electrons. First of all, we know that these electrons must obey Fermi Dirac statistics. So the Fermi Dirac statistic at 0 Kelvin tells us that only electrons up to a certain level are occupied. And this is a probability distribution function. This energy is called the Fermi energy. So this is the Fermi Dirac distribution at 0 Kelvin. This gives us the probability that an electron, how electrons are distributed. And we know that this Fermi Dirac distribution, at 0 Kelvin, this Fermi energy is the same as the chemical potential. This is given by 1 over 1 plus e raised to power e minus mu over kBt. Okay, these are the Fermi Dirac statistics. So electrons, they have a spin, so they must obey the symmetrization postulate and the Pauli exclusion principle. Therefore, by virtue of that interaction, they spread out into levels. And at 0 Kelvin, all levels up to the Fermi level inside a metal are occupied. Okay? Now, if this term energies are much larger than kBt, then this thing boils down to the Maxwell-Boltzmann distribution. Okay? So what we've done so far when we studied paramagnetism, we looked at the Maxwell-Boltzmann distribution. Because those were bound electrons, they were not free electrons, they had different electrons existed in different quantum states, they were on different atoms. Therefore they obeyed the Boltzmann statistics. Now all of these free electrons are indistinguishable and they are in the same sea of electrons, therefore they must obey the Fermi Dirac statistics. So the results will be different from bound electrons. So one, we know the Fermi Dirac distribution. The second thing that we do know is the density of states concept. So the density of states means that if you have an energy E, how many states are available for the electron? So when energy is 0, there are no electrons with energy 0. So there is a density of state which has a square root dependence. So this is proportional to square root E. Now these are the two basic concepts that we should all be familiar with. This I've explained a little bit. Let me spend 2 or 3 minutes on this thing over here because it's important. It's a recap from basic solid state physics. We know that if we have a solid and it's a bound solid of volume V, then if we look at the states of the electrons in the k space, there is a kx, there is a ky. The electrons take up different k values. Right? Likewise in the z dimension. And the volume, this spacing, because of the boundary conditions inside the k space, equals 2 pi over L. So the volume occupied by each state in k space is 2 pi over L cube. 2 pi cube over the volume of the solid. Bigger the solid, the smaller, the closely spaced will be the points in the k space. So these k values tell us the energy of the electrons. Remember that. So the energy of a free electron is characterized by the k value. That's equal to h bar squared k square over 2m. Okay, this is something we already know. And we also know that inside a metal, at 0 Kelvin, there is a Fermi sphere, and all states within the Fermi sphere are occupied. So the length of this vector is called the Fermi vector. Okay? So now what we need to do is we need to find out the density of states. Let's find out Gk. This is the density of states in the k space. How many k states exist in some volume of k space? Okay. So what we would like to do, in k space we draw a shell of radius k of thickness dk. So this is a shell, and we count the number of states inside this shell, and we know that we know the volume that each state occupies. So the volume of this shell is 4 pi k square dk. Each state occupies, so let's count the number of states. This is the total volume available in k space. Each state occupies this volume. So the total number of states is 2 pi cube into the volume of the solid. So this is the total number of states available to electrons inside, total number of k points available to the electrons inside this shell. And you multiply this with 2 because on each k value there could be 2 electrons with opposite spins. This is the spin degeneracy. Okay. So this is GKDK, which tells you the total number of electrons available in this thin shell, GKDK. And this will tell us what GK is. Right? Now, K and E are related. So I can express everything in terms of E's instead of K's. And if I work that out, if I use this expression to rewrite the K's in terms of E's, what I will notice is that GE will be equal to some constant into E 1/2. This is the density of states. These states are available for the electron to be occupied. Okay? And Fermi Dirac distribution tells us the probability that each E level is occupied. And these tell you the number of available placeholders for the electrons. So the number of electrons, so if I take Fe, the curve of Fe versus E, and if I take the curve of the density of states versus E, remember we're talking about 3D solids. For 3D solids does this hold true. For 2D it's different, for 1D it's different. This you learn in solid state physics. So this is a step function with a discontinuity at the chemical potential. This thing is something that goes as a square root. So when so in order to find out whether a really an electron is present at some energy value, I have to multiply these two terms. Okay? So if I take the product of these two terms graphically, so here I have E, here I have Fe, Ge, then I would obtain something like this, right? And if I take the area under this curve, this will give me the total number of electrons up to the Fermi level. And that will be equal to the total number of electrons that are available inside the volume V. Okay? So I take the integral of this thing with respect to E up to EF. I will find out the total number of electrons inside the solid. And that's given by the volume of the solid and the concentration of electrons, or the valency of each atom. If I change the temperature a little bit, what's going to happen is that this curve is going to smear out a little bit. Just a little bit. Increase the temperature, is going to smear out a little bit. Just a little bit. And this curve is going to smear out a little bit like this, if I increase the temperature a little. But this effect is really small. Correct. So this is the background for studying the free electron model. Now in the next lecture what we're going to do is, okay, let's spend 5 more minutes if you don't mind, while we are at it. So, कहते हैं ना कि कुएं पे ले जाएं, फ्रीजर ले गया सिकंदर आजम को, तो कुएं पे जाके प्यासा छोड़ दे तो क्या फायदा? Okay, so with this basic information, what I would like to talk about in the last 5 minutes is spin split bands. Okay, I take this curve over here, this curve over here, and I skew this curve and draw it in this fashion. This is my number of electrons. This is my E. Okay, let's draw GE. Let's draw only GE. And I know that only up till EF would the electrons be populated. So I just rotate this curve, right? I just draw it like this. So I have a band like this. Okay? And this is only meaningful at 0 Kelvin up to a certain energy level, which is called the Fermi energy, which is equal to the chemical potential at 0 Kelvin. Now I have 2 kinds of bands. Suppose I separate out conceptually the spin up bands, the electrons in which the spins are pointing in one direction, from the spins that are pointing in the other direction. Right? So I have 2 kinds of bands. One is the magnetic moment in one direction, the other is the magnetic moment in the opposite direction. At 0 field, these 2 bands do not have a separate existence. They are degenerate, they're just the same. You cannot distinguish between these bands in the absence of a magnetic field, because there's no concept of up and down spin. Because up and down spin means you are defining an axis, but there's no axis because you haven't applied a field. Okay? Now what happens is, you apply a field, you turn on a magnetic field. We're going to see the response of these electrons. These curves come out from the density of states relationship. You would like to find out the response of these bands. One of them spin up band, the other is spin down band. What happens when you turn on a magnetic field? So magnetism manifests itself when non-spontaneous magnetism manifests itself when you turn on a magnetic field. Paramagnetism and diamagnetism are only applicable when you turn on a field. If you don't turn on a field, there is no magnetism. For paramagnets and diamagnets. I'm not talking about ferromagnets. Alright, so now you turn on the field. Suppose this moment is aligned with the field. What's going to happen to its energy? So when we study paramagnetism, if the moment is parallel to the field, what happens to its energy? The energy is lowered. So all of these electrons will lower their energy. And all of these electrons which are anti-parallel, with moments anti-parallel to the field, are going to raise their energy a little bit. How much? Each electron is going to shift its energy by plus minus mu b. Each electron has a moment mu b. Okay? Right now we are assuming that the free electron has an orbital angular momentum 0. Keep that in mind. Okay, so its magnetic moment is purely due to spin. Hence its moment is mu b. So these electrons will lower their energy by mu b. So what's going to happen is that this band is going to shift downwards. Little bit. This band is going to shift upwards. So now I redraw this diagram. One band shifts downwards, the other band shifts upwards. And if a state of equilibrium is reached, then both of these bands are completely filled up to EF. Because otherwise, if this band is slightly higher, electrons will spill over from the higher energy to the lower energy state because these bands are available. So equilibrium is established when this Fermi level latches itself at the same value in both of these spin split bands. Otherwise, if this band is higher, if the electrons occupy space above the Fermi level, then they have empty levels available here, so they can easily come down. They can flip their spins and come lower their energy. So equilibrium is established when this Fermi level is lashed at the same level in both of the spin split bands. Now this energy separation is 2 mu bb. These electrons are up, say alpha beta. Now if a field was off, there is no magnetization because there is the same number of up electrons and down electrons. Now because we switched on a magnetism, there are more electrons of one kind over the other. Okay. So the number of electrons per unit volume of the alpha kind minus the number of electrons of the beta kind, and you multiply each one of them with mu b, will give you the magnetization of this sample. Here n alpha was the same as n beta, so the sample was unmagnetized. Now a magnetization has been built up. Now we would like to calculate these numbers. And for that, we'll do it the next time, but we'll use this kind of integral. Okay, so if I were to, let's do it right, I mean, just do it at it. So n alpha, the number of electrons per unit volume of kind alpha, is given by Fe, which is the Fermi Dirac probability density function. This is like a probability density function. dE, G, now each electron's energy is lowered. So this is E minus mu bb. You find out the whole band is shifted. So the density of states curve is shifted downward by mu bb. And you would like to integrate from minus mu b to EF. Okay? Now this is really small. This mu BB is really, really small. Okay, so I put this equal to 0. And beyond EF, the Fermi Dirac distribution is 0. So I can put this equal to infinity. Because the Fermi Dirac distribution is step function, it goes to 0 beyond EF. So I can take the integral all the way up to infinity. Because here the probability density is 0 anyway. So this just eases out the integrals. Likewise, n beta is going to be equal to 0 to infinity dE Fe GE plus mu BB. Now I need to subtract these objects. When I subtract these objects, let's do that. It's easy. N alpha minus n beta, which gives me the polarization of this magnet, right? It gives you the net difference of the spins of two kinds, which will lead to magnetization, is 0 to infinity dE Fe G E minus mu BB minus G E plus mu BB. Now, since mu BB is very small, I can use the Taylor series expansion to write this down. I can write down the derivative of G with respect to E and multiply it with the difference in the energy, which is 2 mu BB. So this turns out to be 2 mu BB. Hello. 2 mu BB, 0 to infinity dE Fe and this thing is the derivative with respect to E of GE. Alright, so I have to compute this integral and then I have to multiply this with mu B to get the magnetization. So let's compute this integral. Just going to take 2 minutes. N alpha minus n beta equals 2 mu B B. I do integration by parts. Fe, the integral of this thing, which is GE, from 0 to infinity, minus 0 to infinity GE, the derivative of the Fermi Dirac distribution. DE. Now when this is infinity, what is this function? 0, because this is 0. When this is 0, what is this function? 0, why? Because this is 0. So this thing is 0. Now I'm left with the task of finding out the derivative with respect to E of Fe. Now if you look at the curve for Fe, this is E, this is Fe. Everywhere the derivative is 0. It's not 0 only here. Here the derivative is a Dirac delta function and a negative Dirac delta function. And that Dirac delta function only exists at EF. So this thing over here equals minus the Dirac delta function at the value of EF. So this turns out to be 2 mu BB. This minus goes away with this. 0 to infinity GE Dirac delta function E minus EF. Now it's simple, I use the sampling theorem, the property of the Dirac delta function. The magnetization is 2 times, I need to multiply this with n, small n, mu b, b, g, e, f. Oh, and one thing I forgot, there's already a mu b here as well. This is, sorry, mu b square. This becomes mu b square. This is the magnetization of the sample. And if I would like to find out the susceptibility chi is m over into mu naught. So this is 2 mu naught mu b square b equal, divided by b, m. Alright, g, e, f. Right? This is the magnetization of the sample, right? Temperature independent. But you might argue that I took the Fermi Dirac distribution to be a step function. Even if I included that small temperature dependence, the temperature dependence is going to be really, really small. Is this positive or negative? Positive. So this is paramagnetism. Free electrons inside a metal, they give rise to paramagnetism. This is called Pauli paramagnetism. There is no B dependency in the susceptibility, in the magnetization, yes. Second thing is it depends upon the density of states at the Fermi level. How many electrons exist at the Fermi level? That gives rise to magnetization. That is independent of the temperature. Depends upon other things, right? G of EF can be shown to be inversely proportional to the Fermi level. This is something you learn from solid state physics. So if I would like to write this in its final form, this equals (3 over 2) mu naught mu b square 3 over 2 n over EF. This is a relationship that comes from basic solid state physics. I think I could derive it, but I don't have the time for that. 3 times mu naught mu b square n over EF. This is the Pauli susceptibility, the Pauli paramagnetism for a sea of free electrons independent of temperature. Okay? For bound electrons, normal paramagnetisms, isolated spin half particles, we know that the susceptibility in the Curie's law is given by mu naught mu b square n over, I think, 2 kBT. This is something we've derived previously. There is no 2 here, right? Here there is a temperature dependence. This is Curie's law for spin half, but there is no temperature dependence here. If I would like to write, sometimes people write this Fermi energy as Kb times the Fermi temperature. Since Tf is much, much larger than T, the Fermi temperature is much, much larger than T at all temperatures. Even up to the melting point, the Fermi temperature of the 5,000, 4,000, 6,000 kelvins, the Fermi energy is so high in metals as compared to room temperature. So the Pauli Paramagnetism is a much smaller effect than the magnetism due to isolated bound electrons. But nevertheless, it's an important effect. So this finishes our discussion of magnetism of free electrons. In the next lecture, we're going to look at different other things. We're probably going to look at Landau diamagnetism. Okay, what if we include the effect of an orbital magnetic orbital momentum for the electrons, free electrons, okay?